Good morning, everyone. This is Dr. G. Amarendra Rao, Department of Mechanical Engineering, Vigyan Bharati Institute of Technology, Hyderabad. In today's session, we'll be discussing about composite cylinders subjected to convective environment. As a matter of fact, a cylinder which is made up of number of materials is termed as a composite cylinder. Typically, steam pipes carrying a hot fluid like exhaust gases, a cold fluid like a refrigerant, are typical examples of composite cylinders. As the pipe is subjected to fluid on both of its surfaces, we'll be experiencing convection both on inner as well as outer surfaces. In this session, it's intended to analyze composite cylinders involving combined modes of heat transfer. Having said combined modes of heat transfer, it's going to be conduction with convective boundary conditions. Now we'll pick up a cylinder made up of three materials to begin with. It could be anything more than one, but we are beginning with three materials having thermal conductivities K1, K2, K3 respectively, and the radii of the cylinder are R1, R2, R3, R4 respectively, and the length of the cylinder is L normal to the board. If it's not given, one can take it as a meter. So per unit length, one can make the calculations. Now we presume that the inner surface is subjected to a hot fluid, so that there will be heat transfer in the positive radial direction at a temperature of Ti with a convective heat transfer coefficient of Hi. And the outer surface is subjected to a cold fluid like air or coolant, something like that, at a temperature of T0 with a convective heat transfer coefficient of H0. So that we are going to experience heat transfer radially outwards. At the same time, we can as well have otherwise. We can have a cold fluid inside like a refrigerant and hot air outside. In that case, everything is same, but the direction of heat transfer is going to be opposite, reverse. So the result is going to be negative, indicating that Q is in the opposite radial direction or decreasing radial direction. So the physical arrangement of the cylinder is shown over here. So this red color indicates the base material of the cylinder, maybe cast iron, maybe aluminium, of inner radius R1. Some thickness plus R1 will give us R2. Then K1 is the thermal conductivity of the base material. Then we incorporate one layer of insulation having some thickness. Thickness plus R2 will give us R3. Then to satisfy some requirement or the other, we are going to have another layer of insulation. And these insulators are having thermal conductivities of K2 and K3. Then thicknesses will be available to us. Accordingly, we can estimate the radii. Then inside a fluid is flowing, creating an environment of HITI. HI is the inner heat transfer coefficient, Ti the inner fluid temperature, and the outer surface is subjected to a fluid having a temperature of T0 and a convective heat transfer coefficient of H0. Then in order to have continuous heat transfer at a steady rate, we assume that Ti is the highest temperature, T0 is the lowest temperature, sandwiched by surface temperatures T1, T2, T3, T4. As a matter of fact, we have only Ti and T0, and we'll be looking for two parameters in our analysis. One is heat transfer rate, the other is surface temperatures. And we'll be having driving force, temperature difference all along. So Ti is more than T1, promoting inner convection. T1 is more than T2, promoting conduction through first layer. And T2 minus T3 the basis for conduction through second layer. And T3 minus T4, this temperature difference is the basis for conduction through third layer. Then ultimately T4 minus T0 is the driving force for the outer convection. So we'll be having sustaining continuous temperature differences all along. Now, with the definition of this problem, we'll be analyzing with a couple of objectives. One is to estimate the heat transfer rate. The other is to predict the unknown surface temperatures so that we can find out the driving forces available at each and every segment of the composite cylinder. Then this can be done by two popular methods. One is the concept of electrical analogy. The other is the concept of overall heat transfer coefficient. And we get to realize that both the methods complement each other. When you talk about electrical analogy, we replace the given system by an unlocked circuit diagram containing number of resistances. And in general, we'll be experiencing 1 plus n plus 1 number of resistances. One is the inner convective resistance, and last one is the outer convective resistance, and in the middle we are going to have n number of conductive resistances, where n stands for number of layers in the system. Since our system we have 3 number of layers, n is equal to 3, so we will be having 5 resistances, and all these resistances will be operating in series since the layers are placed one after the other. In the other sense, first there will be inner convection, then conduction, then conduction, then conduction, then convection. So nothing is happening in parallel or in tandem. And the corresponding circuit diagram is shown over here. And before that, we ignore the radiation effects just to simplify the life. But even if radiation is there, absolutely no issue. We can take care of it as we did in the beginning of our discussion. If at all radiation is there between Ti and T1, we'll be having two parallel resistances. It is as simple as that. But when we ignore the radiation, we'll be having all the resistances operating in series. R1, R2, R3, R4, R5. We can note that R1 is working between Ti and T1, R2 is working between T1 and T2, and so on. And here R1 represents inner convective resistance, which is given by 1 by HIAI, that is 1 by HI 2 pi R1L. We realize that AA stands for the inner surface area of the composite cylinder. R2 is log R2 by R1 by 2 pi K1L, which indicates the conductive resistance offered by layer 1. R3 is log R3 by R2 2 pi K2L, degree centigrade per watt, represents the conductive resistance offered by second layer. And R4 is log R4 by R3 2 pi K3L, the conductive resistance offered by third layer. And we may note that outer radius of first strip is the inner radius for second strip. Outer radius for second strip is the inner radius for third strip. So absolutely no gap, no resistance between the two materials of the composite cylinder. So that care we will be taking. And finally, we'll be having R5, which is 1 by H0 A0, that is 1 by H0 2 pi R4L. Which stands for outer convective resistance. And as I was telling earlier, AA stands for inner surface area, the area available for the inside fluid, which is given by 2 pi R1L. On the other side, A0 stands for outer surface area, which is given by 2 pi R4L. And we can notice that A0 is going to be much more than AI. And since all the resistance are operating in series, we can blend them together to get the equivalent resistance of the system. And Q is simply the ratio of del T overall by R equivalent, and del T overall represents the overall thermal potential available in the system, and R equivalent is equivalent thermal resistance. which is simply the sum of individual resistances, and having known R1, R2 and so on, we can substitute for them in R equivalent, and we may note that 2 pi L is common everywhere, and when we take 2 pi L common, and we are going to get the expression for R equivalent as given by equation 1. That is, you begin with inner convection and terminate with outer convection. In the middle, we are going to have as many conductive resistances as the number of layers. If at all we have a composite cylinder only with 2 layers, we stop conduction here. Then we'll go for 1 by H naught R3. If at all we have one more layer, then the corresponding conductive resistance would have been log R5 by R4 by K4. Area would be enhanced, it's going to be 1 by H naught R5. So that way the conduction terms are fragile. You can have as many as you wish. Then one can substitute for del T overall and R equivalent in the expression for Q to get the general expression for the heat transfer rate, which is simply given by 2 pi L del T overall. 2 pi L will go upstairs upon all these terms beginning with inner convection, ending with outer convection, in the middle number of conductive resistances. So this equation can be used to get the radial heat transfer rate. If at all del T overall is negative, that is Ta is less than T naught, you are going to get a negative result, indicating that the direction is opposite. Magnitude remains the same. And we may note that in the process of getting Q, we are able to eliminate surface temperatures. Del T overall is enough for us. And del T overall simply indicates Ta minus T naught. Both of them are available to us. Therefore, Q can be calculated without the knowledge of the surface temperatures. Now we do the reverse engineering. In order to obtain the surface temperatures, we carry out energy balance across each segment of the system, which means that Q also should be equal to inner convection. Q should be inner convection. Q should be equal to conduction through first layer. Q should be equal to conduction through second layer, and so on. After all, we are talking about steady state heat transfer, one-dimensional heat transfer. So we write Q as Ti minus T1 by R1 to get T1. Q as T1 minus T2 by R2, we get T2, and so on till we reach our end goal. So that's the meaning of energy balance. So we write Q as Ta minus T1 by R1, which will give us T1. Q as T1 minus T2 by R2, that will give us T2, and so on till we realize that we have obtained all the surface temperatures. And this analysis can as well be carried by the concept of overall heat transfer coefficient U, which has been introduced in the previous session. And U represents the rate of heat transfer per unit area per unit overall thermal potential. When it comes to composite walls, there is only one area, therefore one U is enough. Because composite walls, everywhere the area remains the same. This is the area A, this is the area A, and so on. But when it comes to composite cylinders, composite spheres, we have got a couple of areas: inner surface area, outer surface area. Accordingly, it becomes customary to introduce corresponding overall heat transfer coefficients. As a result, we can write Q as Ui Ai del T overall. That is Ui 2 pi R1L del T overall. Q as well can be written as U naught A naught del T overall. That is U naught 2 pi R4 L del T overall, where Ui is known as the inner overall heat transfer coefficient, and U naught stands for the outer overall heat transfer coefficient, which means that Ui is the overall heat transfer coefficient based on the inner surface area Ai. On the other hand, U naught is the overall heat transfer coefficient based on the outer surface A naught. A little consideration shows that ui and u0 are dependent variables, which means that when you compare equations 3a and 3b, we get to notice that when you compare these two equations, we get that r1 ui is equal to r4 u0, because 2 pi l del t overall is common everywhere. So the product of innermost radius times ui should be equal to the product of outermost radius times u0. And since R1 is much inferior to R4, it follows that Ui is much more than U0. Mathematically, this is the reason why Ui is more than U0. And physically speaking, Ui is more than U0 due to the fact that the inner surface area is very less compared to the outer surface area. This area available for inner fluid is very less compared with the area available for the outer fluid. However, both the surfaces must handle same heat load. If heat transfer rate is some 1.5 kilowatts, both the surfaces will have to handle the same load. And to mitigate for the fact that AI is very small compared with the A0, we are going to have Ui more than U0. With the physical reasoning why Ui of a radial system, maybe a composite cylinder or composite sphere, is more than U0. It's only to compensate for the reduced area available for the inside fluid. Then we get to know that Q is already available in terms of basics, equation 2, and Q is available in terms of Ui and U0. And when you simultaneously look at equations 2 as well as equations 3a, we will be getting the expression for Ui. That is a simple mathematical manipulation. That is 1 by Ui is equal to 1 by Hi, beginning with the convection. R1 by K1 log R2 by R1, which corresponds to the first layer. R1 by K2 log R3 by R2, which corresponds to the second layer. R1 by K3 log R4 by R3, which accounts for the third layer. If at all you have one more layer, R1 by K4 log R5 by R4. So you can have as many terms as you feel that you need. At the end, it's going to be R1 by R4, 1 by H0, which stands for the outer convective term. And by a similar fashion, one can have a simultaneous look at equations 2 and 3b to obtain the expression for outer overall heat transfer coefficient. And both the equations are alike, but for the fact that R1 is replaced by R4. And you can see the difference between equations 3a and 3b. Only change is that this is inner surface area 2 pi r1l, whereas this outer surface area 2 pi r4l. And once we replace r1 by r4 and we carry out same analysis, we obtain the expression for the outer overall heat transfer coefficient. And further, one can have a simultaneous look at equations 2, 3a and 3b to get a relation among ui, u0 and r equivalent, which means that all these three derived parameters ui, u0 and r equivalent go together. If you have one of them, it's as good as you have remaining two. So that way you can always calculate ui by doing all the efforts, then it's as good as you have u0 and r equivalent, or you can find r equivalent to obtain ui and u0. And once we obtain ui and u0, you can always go ahead with the calculation of heat transfer rate. And once you get heat transfer rate, we can go down to the basics to get the surface temperatures, in the sense that we can write qi heat transfer rate as inner convection, that is going to be hi ai ti minus T1, right? Inner convection, you can calculate T1. And this Q is also equal to 2 pi K1L upon natural logarithm of R2 by R1 or T1 by T1 minus T2, that is conduction through first layer. This is going to give us T2. So write the expression for convection, conduction, 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 and so on to obtain the unknown surface temperatures and to unlock the surface temperatures which are otherwise unknown to us. Then you can always draw plots, graphs. Remember, this is going to be a logarithmic curve, this will be a logarithmic curve, this will be a logarithmic curve, having different slopes depending upon the material and the thickness. And this is the very complex one which will be discussed at the time of convection. So this depends upon the boundary layers that we are going to talk about in detail. So this is the gist of the composite cylinders. Now in our next session we talk about composite spheres, followed by numericals on all the composite systems. So with this we stop our discussion. Have a great going. Thank you.